moving forward from here, the next thing that we can then think of is, obviously there was nothing preventing me from having both multiple masters as well as multiple slaves at the same time. If I have m masters and s slaves, I would have S1, S2 up to S subscript capital S. I would need arbitration logic on this side and decode logic on this side in order to decide who gets to talk to what. Okay. Now of course comes the question, what about the efficiency, what about the throughput, what is the best communication pattern that I can actually use over here? Because one thing, the way that I have drawn this right now, it clearly shows a problem. There are m masters and s slaves. At any given point in time, how many of them can talk to each other? Only one pair. Okay. So by the way, before we go further, one thing I just want to say, can you think of any peripheral that could be both a master and a slave? Why would you say an ADC is a master as well as slave? An ADC is almost certainly a pure slave, in the sense that it's just whenever the CPU wants, it gets data from the ADC. Even SPI, SPI is actually a bus by itself. So an SPI is not in itself a peripheral. An SPI is an interface. Okay. So in fact, the buses that we are drawing over here, SPI could be used in order to implement the interface part of it, but by itself it is not a module. DMA on the other hand, right. So what is DMA? It's direct memory access. We will look at that a little bit more, especially in the context of actually implementing the hardware later. Direct memory access is specifically introduced in order to do one thing, which basically says there can be situations where I just want to copy a large amount of data from somewhere to somewhere else, from some bunch of memory locations to another bunch of memory locations. It's possible that both of those blocks of memory are in the actual RAM itself, or one block could be in the RAM and the other one could correspond, let us say, to the Ethernet device, right, or it could correspond to the video display, right. In such a situation, essentially what I have is that DMA module has to behave in two ways. One is, it has to be able to get instructions from the CPU, so it becomes a slave, right. That is, when a CPU decides that it wants to talk to this particular, that it wants to set up a DMA transfer, it has to be able to talk to the DMA module. On the other hand, once the CPU has given the instructions, the DMA then needs to take over the bus and actually say, I want to transfer data from A to B without the CPU getting involved. Okay. So it's possible to have one device which is both master as well as slave, right. But in this case, what we are going to assume is that I will just logically split it into two parts, put the slave interface on the right side, master interface on the left side, and treat them as two separate interfaces, even though they belong to the same hardware module, right. As long as I just make that logical separation between them, there is no conflict. I can treat the same module both as a master and as a slave. Now, with that out of the way, what we can say is, if I have multiple masters and multiple slaves, with a shared bus like this, at any given point in time, only one pair can talk, and this is bad news, especially as the number of masters and number of slaves goes up. Okay. So what can you do about it? What would you, can you propose any way by which this could be solved? One possibility is multiple buses. Okay. So let's in fact, now I am no longer even going to draw masters and slaves separately, I will just draw them as modules, right, and assume that any one of them could be either a master or a slave, it does not really matter. Okay. So what I am saying is, I have this simple system over here which has M1, M2, M3. Okay. What if I also put another bus out here and just connect all three to that also? This is probably a bad example because there are after all only 3 devices, so let me just add one more over here. Now what I could have is, I can think of a situation where, let us say, M1 is talking to M2 and at the same time M3 is talking to M4. Both communications can go on at the same time, because they are happening on different buses. Okay. It still is not a trivial solution, because now M3, when it wants to communicate with M4, first has to look, it will probably look at the same bus that M1 is already using, then decide I can't use this because it is busy, let me go look at the other bus. Okay, that is free, now let us use that. It complicates your internal logic a little bit, but not as much as you would think, because after all, this whole business of I will go look over here, then do this, it is not like somebody is running around doing this. There are electrical signals that automatically just flag, okay, this is not available, the next one goes high and activates that the other bus can be used. Okay. But it does obviously complicate your internal logic. It is possible to do at the expense of internal logic. You could also have another situation where, for example, M1 talks to M4 and M2 talks to M3, that is also possible, right. So, multiple different combinations of this sort can happen at the same time, right. It still does not address the question of whether M1 can talk to M2 and M3 at the same time. That may or may not be possible, that is now more a question of how M1 is implemented. So, multiple buses, in other words, is one way of doing it, right. Another thing that can be done is actually to say, let me be a bit more clever about this. Can I think of splitting a bus? Okay. So, what does that mean? A split bus is actually a bit more tricky. What it is basically saying is, I have M1 over here, M2 over here, M3 and M4. I have a bus, but now what I am going to do is break this and have some kind of a bridging module in the that goes between them. What does this bridge do? Effectively what it accomplishes is that I can now communicate between M1 and M2 and M3 and M4 at the same time. But if I wanted to do, let us say, M2 to M3, at that point this is not going to work. So, the question becomes, how do I do M2 to M3 in the first place? The bridge has to get activated. I need to indicate that I need to make a communication across the bridge. There will be some logic in that bridge that basically says, okay, now I need to connect the two sides together and allow the signals that are coming from, let us say, whichever is the master, to go across the bridge to the other side, get decoded over there and communicate to the other side, right. So, the result of this was that if I was just talking between M1 and M2 and M3 and M4 respectively, then they can go on completely in parallel, right. But the moment that I want to go across that bridge, that becomes the bottleneck, right. And unless I am able to sort of, and in that case effectively what it means is that I am back to my single shared bus kind of topology. I could combine this, I could have split as well as multiple buses, right. Obviously this starts to get even more and more complicated, right. Another place where this is sometimes done is not just in something called a split bus, you also have something called a hierarchical bus, right, where again the story is somewhat similar. You have M1 over here talking over a bus to, let us say, memory, and you have a bunch of other peripherals over here that are basically like the keyboard and serial port, right. But over here I have some other things which are essentially, let us say, Ethernet and display. So, can you see what is common to the stuff that is on the left versus on the right? So, this M1 is basically the CPU, let us say. So, the CPU, memory, Ethernet, display all on the left hand side, keyboard, serial port on the right hand side, and there is a bridge in between them. What do you think separates the two sides? I mean, why would I make them two separate? Typically at what speed is a keyboard responding? It depends on how fast you are able to press buttons, right. How fast do you type? Pretty much the fastest that you can do is probably 100 key presses per minute, okay. that's, I mean, that's literally, I mean, almost the mechanical limit of the speed at which you can type. Okay. So if that's the case, 100 key presses per minute is nothing. I mean, that's like barely, less than 2 keystrokes per second. Okay. Even if I just keep a key pressed, it's probably only a few it translates into a few key presses per second, not thousands, maybe 10 or 20, somewhere around that. Okay. Which means that the rate at which data is coming from the keyboard is on the milliseconds time scale, right. It's like a few tens per second maximum. Serial port, maybe a bit more than that, you might go up to kilobits per second, but that's about it. Ethernet on the other hand, you might be actually talking about data transfers in the gigabit per second range. Main memory, of course, the CPU wants to talk to memory as fast as it can. And the display unit also requires a large amount of data because you are trying to refresh that screen 30 or 60 times per second. Okay. So everything on the left has a huge amount of data that, and any time that it gets activated, the data needs to get transferred at a very high speed. Okay. Whereas the ones on the right are going to be very slow. What's the problem there? The biggest problem is, let's say that the CPU tries to read something pressed on the keyboard. It issues a request to the keyboard, response comes back 10 milliseconds later. For that 10 milliseconds, what's the CPU going to do? It can't just sit idle. It could have done a few million instructions within that time. Okay. So those kind of things, you want to separate them out. You might even have a situation where I just run this at a slower clock, and this is the high performance side, right. And you could take this further. You could basically have the splitting of the buses taken to multiple levels, where I first have a split and then further split it into other peripherals. Unless there is at least one master on each of those splits, it doesn't allow you to increase the bandwidth of the bus. But in a case like this, it might not really be about increasing the bandwidth, it might just be about separating it out and preventing the bus from being locked up by somebody. Okay. So all of these, in other words, are different architectures, different structures that can be used in order to implement the basic topology of a bus. Okay. Then comes the question, what are you going to do with it? Okay. And that essentially leads to this concept that of what's called transactions. Okay. So a bus transaction essentially deals with multiple stages. Okay. And especially when we are having a situation where there is something like a CPU, a master, or multiple CPUs, multiple masters talking to a bus, and they want to get data from the other side, it goes through a set of phases, signaling phases. Okay. The typical flow is something like this. There is something called a request that comes from a master. The bus will then issue a grant signal, and then after that the master will actually transfer the additional control signals, possibly the address. Finally, there will be transfer of data. Okay. All of this together would typically become one transaction. So in other words, if the CPU wanted to read some data that is sitting in the memory, the actual process that goes through is, it first has to request access to the bus arbiter will, this will be done by the bus arbiter, right, which takes care of bus arbitration. The arbiter would say, okay, fine, now you can talk. Then the CPU puts out the memory address from which it wants to read, and finally the slave, which is the memory controller in this case, actually gets the data back and returns it. So all of these together form one transaction, right. And if you typically look at it, the timeline of a transaction could be something of this sort. Usually these are represented using some kind of timing diagrams. So, the most important one is basically the clock. Along with that, of course, any bus will also have some kind of a reset signal associated with it, which is implicit. I am just assuming that all digital logic has a reset, so I am not mentioning that separately. But the process would go something like this. There would be a request signal which would go high, and assuming that the clock is triggered on rather all the elements are working on the positive edge of the clock, it means that if the request signal goes high somewhere here, it will be seen at the next positive edge of the clock by the bus. Okay. When would the grant signal come back? If assuming that the bus is free, a grant signal would then go up here immediately after that. Okay. And then this could take care of putting the address. Depending on how it interprets the grant signal, either it has to wait until the next clock cycle so that it actually sees that the grant signal has been given to it, okay, or it might do some kind of combinational logic and say that the moment the grant signal is high, the address is also made high. So, it essentially has a dependency from here to here. Then all this is from the master, right? It has gone to the bus. Let us say that the slave was a memory controller. This address then gets passed on to the memory controller, it has to retrieve the data and finally come back. In the ideal situation, in the very next clock cycle the data will come back, but it is possible that the data which is being read back actually comes several cycles later, okay, and let us say comes somewhere out here. So, this is essentially the complete sort of flow of signals that would happen for one transaction to take place. This is an example of one read transaction from a module like a memory block, right. So, the master would put out a request, one cycle later it would get a grant, then it would put out an address, a few cycles later it would get back the data. This part that you see over here essentially is handshaking overhead. Or arbitration overhead. Okay. Why are we calling it overhead? Because in the ideal situation, if it was only one master and one slave, I could have just been reading on every clock cycle. But now, even before I can issue one read, I first need to get access to the bus, right. This is the simplest form of a transaction. I put out a request, I get the grant, I put out the address, wait for some time, get back the result. If every transaction was like this, you can imagine that it would be horribly inefficient, right, because for every value that I want to read from memory, first I have to send out a request, wait for a grant and then read one value. So, that is 3 cycles gone anyway. If the memory takes a long time to return with the value, that is so many more cycles also gone. Okay. So, in the simplest form that I can implement a bus like this, it is going to be terribly inefficient. Obviously, there are ways around it. Even from the way I described it, we can think of ways around this. One of them is to use a so called burst mode of transaction, right. So, burst transactions will essentially say request, grant, address and multiple data. So, the number of data would be specified in the control signaling, right. So, for example, what I can do is I can say I want to burst read 4 values from memory. Okay. There would be one request, one grant, one address, but 4 values will be returned from memory. Okay. So, I am able to take the fact that I had this overhead of request, grant and putting out the address and split it out over 4 accesses. right? I could go further, maybe make it 8 accesses, maybe make it 16, I could keep increasing that number. The point is, after a while it becomes counterproductive, because I am not always trying to read bursts of data, right? So, I do not want to unnecessarily provide for very huge bursts. I would much rather have some reasonable size bursts, let us say up to 16 values or something of that sort, and then if necessary, take that additional overhead of again request grant after that. The other problem with, so the problem with having a burst is that during that time, that is the only activity that is happening. So, if I ask for a very long burst, let us say I ask for a 1 kilobyte burst, right? For the next 1000 cycles, the bus is occupied just transferring that data, nobody else can talk. Whereas, if I limit the size of my burst and say this is at most going to be up to so many clock cycles, so 16 cycles or so, right, then I still have reduced the overhead of my request grant and address signaling and spread it out over 16 data transfers, right. So, burst transactions are sort of the most obvious but important improvements that are made on the bus, right. There are a few more that we will consider next, basically something including splitting transactions and pipelining them, right, which again are fairly obvious, but it is worth sort of understanding how they get implemented in a little bit detail.